Bring me a little water, Sylvie. Bring me a little water now. Bring me a little water, Sylvie. Every little once in a while.
This is Louise Cetera. I'm trying to give her a shout out because I think she's one of the great voices. This is her singing a song called Sylvie. She's right up there with the great women's voices like Karen Carpenter and Katie Lang, and another one you haven't heard of, Chloe Foston. You ought to watch out for Chloe Foston. She's got an amazing voice. Anyway, we got to get into what we're supposed to be talking about. Hope you enjoy that. Louise Cetera. Okay, so today I'm going to talk about something called a breadboard companion. I have all my students work on breadboard companions. This is a board that they can put together. It's like their first soldering project. Most of them have never soldered before, so this is a really great project. But this board is a lot of things, and I also want to give a shout out to the Breadboard Companion Company. I've been using this for years. I love it. Students love it, and it's a good starter board. What's it good for? Well, let me see if I can get that running. It is a power supply. It is a power supply where you can put anywhere from 9 to 20 volts in, and it will give you an output of 5 volts or 0 volts or 9 volts. It also delivers a clean square wave clock pulse that is a variable rate. You can change the rate. It's also for circuit testing. It has 4 switches and it has 4 LEDs, and it can plug right into a breadboard. Students love building them. They get to build them, and I let them keep them because these things are cheap enough, and it is not cheap. They're inexpensive, but it's a good quality board. I've been working with them, use about 100 a year, and I find them very easy to troubleshoot, very easy to assemble, and students really enjoy them. Now, before we get into that, I want to talk a little bit about the first thing I talk about with students just before this is safety. We do a little safety training, and the state that I live in requires students to get 100% on safety tests, or they get a 0. So it's either 0 or 100. Some of the things we talk about are following all written procedures, MSDS, Material Safety Data Sheets. That's what that stands for. Those are all online. We used to keep them in a book, but now they're all online. Don't have to worry about it. Other things we talk about is keeping the work area dry, avoid wearing jewelry when working on electronics. Always assume that circuits are live. Always have an assistant guard the main switch when you're working on other things, repairing. Fire extinguishers, always use a Class C if at all possible, never a Class A, which just sprays water and makes the situation worse. Class C is the fire extinguisher you want to use. Don't use power tools of any kind unless properly instructed on them. Always wear safety glasses. Take time to do the job right. No horseplay. Keep your work area clean. I talk a little bit about lead poisoning because solder is, 60% lead, 40% tin. So they always want to know, is this poisonous? And I say, here's what you need to know about that. When you're soldering and holding that lead in your hands, fight the urge to lick your hands until after you wash the lead off. And if the smoke from the solder tries to go in your nose, move your nose. Also, it's important to say, because we wear safety glasses for a lot of reasons, it seems like this is not an unsafe thing, but even just trimming wires can make projectiles. And if I've missed any safety issues, please feel free to message me and or email me. This is, I didn't say it at the beginning, I'll say it now. This is Aaron Jerome at Jerome Electronics, and you can email me at jeromeelectronics@gmail.com if you feel like you want to, or you can just respond to the video. Okay, what do students need? Well, these are some of the things they need to have to get ready for building this thing, this breadboard companion. We need some diagonal pliers, some needle nose pliers, a small screwdriver, a little bit of solder, soldering pencil, because a soldering iron is a big one, right? A damp sponge, some tape, and some safety glasses. Those are generally what I have my students pull together. These are all sitting on top of a masonite board, which has got a surface on one side for whiteboard markers, but since I've dinged this one up, I usually use the back side, the brown side, but since I've dinged this one up and it's easier to see on the camera, I think I'll try using the white side this time and maybe try not to beat it up too much. Okay, going to clean that board off because I'm going to show you the actual breadboard companion, how it comes in the mail when you order it. When we get this in the mail, it comes in a little package like this, an anti-static bag, and the first thing I do is give the students a little plastic container and say, okay, dump it all out, but don't lose any of the pieces. So that's what I'm doing now, dumping everything out, and hopefully not losing the pieces. I'm going to have to pull that breadboard or that circuit board out of there too. Sometimes it's a little resistant, but not bad this time. There it is. This is the circuit board. It is a circuit board that's been designed by John. I can't remember his name, but he designed it, and he actually trained me, and his name will probably come to mind soon, but if not, I hope maybe somebody will email me and tell me his last name. But John is his first name, and he designed this specifically for teaching this electronics course. Okay, so one of the first things I have students do is write their name on this, because if you've got 100 students and they're all working on this project, some students that were absent yesterday will think, when we introduce this project, this happened to me last week. The student came in, oh, I don't have one, and they just went and grabbed one that happened to be another student's and started working on it and messed it up really bad. And so we want to keep from doing that by putting students' names on there. And so I'm going to put this name on here. That's a good place to put names. Mahatma Jones, you can put class period on there, or day, or whatever, seat number, whatever you have. This is good enough for now. And now we know it belongs to Mahatma Jones. Okay, so I'm going to take all of these parts out so we're not confused by them, put them in the box, in the project box. Don't want to lose them. And get everything off the board here that we don't need. And we'll start. The first thing that we're going to start with is something called sockets. Now, if we were to take integrated circuit chips and just solder them to the board, some students are going to solder them backwards, some students are going to solder them with a pin folded under and solder them wrong, or maybe they'll burn out, and we don't ever want to have to unsolder these. So what we do is we solder a socket into the board. This is actual chip right here. And that's the thing with the numbers on it. We won't do those until very last. We want to be done soldering before we put those in. But let's take this first chip out, or this first socket out. And an important thing about this socket, I don't know if you can see it, but there's a little notch right there. And on the board, there's a picture with a notch there. And even though it'll work backwards, I tell students, let's make sure the notch is the right direction, because there's also a notch, and that's the important thing, there's also a notch on the breadboard companion, and that has to be the right direction or it's not going to work. Now what I'll do is I turn that over, I'm still hanging on to it, and I will use a pair of pliers or something and just kind of bend a couple of those wires over, and that will hold it in place for soldering the rest of them. But before I do, I'm going to put the other socket in, the one for the smaller chip. That chip that we put in later will be a 555 timer chip that will give us the signal for the square wave. Turning that upside down and just using the screwdriver to bend a couple of those over, and that will hold them in place so that we can solder those on there. Okay, so now I'm going to need my solder. I usually give students maybe a couple feet of solder for this project, and if they run out, I'll give them more. And that's what I have here. I got my solder. And I'm going to solder. I wonder if maybe I ought to zoom in on this a little bit. You can see a little bit better. And that's pretty good. I wonder if it'll focus any better. I guess that's pretty good. Okay, so I'm going to solder the small one here. I tell students when they first solder, put the soldering pencil on and touch both the pin that goes through and the little piece of metal. If you have to hold it there for more than 15 seconds, it's too long. I've had students hold it on for 2 minutes at a time, and that's enough to melt the board itself. So it's probably best to only hold it there. And if you time out 15 seconds for students, you'll find that's a long time. Now, I get all kinds of different solders when I do it this fast. One thing I often do, and especially will tell students to do at the end, is just remelt and freeze those pins, and that will make sure that we've got a good solid connection there. Doing the next ones, again, this is difficult for starting students. They've never done it before, but it's just a matter of put the soldering pencil on the pin, jam the solder underneath where the pencil is and the rest of the metal there. Okay, and you saw me touch it there. It wasn't hot. It cools very fast. Getting down to the last two. Okay, so now I've got those sockets in there. Doing a quick remelt and reset. And you don't have to do this now, but generally if there's problems, I'll have students go ahead and do it again at the very end. This is the next component. It's the voltage regulator. Basically, what it does is, if you look on the front of the board, it says you should be able to plug in anywhere from 9 volts to 20 volts, and this voltage regulator makes sure that it's always only 5 volts. And if you look really closely at this, you can see that the wires are wide and then they go narrow. If you will take a pair of needle nose pliers and go across those points where they go narrow, see if I can show you that now. I'm going to shove it in just a little more and get to that point where they are narrow, just going narrow. And once you have that, make sure this heat sink is behind, not on the front, and just bend it 90 degrees, right there like that. That puts all of them at 90 degrees. And if it's not 90 degrees, you can bend it with your fingers to get it into place a little bit closer to 90 degrees. Once you've done that, it goes right there in the board. And so I'm placing mine in and pressing it down. Now, this voltage regulator basically, if you've bent it right, it should line up with the hole underneath there. This voltage regulator, what does it do? Well, it takes the voltage and it reduces it. The voltage is basically, well, it's an electron that's filled with photons, and those photons are making it's a lot of explanation, but in my mind, the photons make the electrons want to wobble or oscillate more, meaning they demand more personal space, and that causes them to push electrons beyond the space, say, inside a battery. We have to move some of those photons, and photons are really nothing but motion. Their motion, their light, their heat. We're going to remove some of those through this voltage regulator. The 9 through 20 volts will go in through this first pin. The second pin is the ground, and out comes 5 volts. How do we get rid of those? By eliminating heat. That's what this does. The voltage regulator is not a transistor, but it has a lot of transistors inside of it. And it's kind of like a solid-state variable resistor. Now, for what we're going to do with it, we need more. This is a heat sink, and that's where it will dissipate the heat, but we're going to need more dissipation than that. So in this kit, another heat sink has been provided, and I'm going to slide it underneath. But anyway, you can see that I got it in there. The other heat sink is in there, and I'm going to line it up so that those holes align. And then the next thing I'm going to do is get into my parts box and find a little tiny nut and bolt, or nut and screw. I'm going to take the screw off of that nut, and I'm going to push the nut up through the bottom, through those holes, and now you can see it's up through the holes, and it's coming through the top. And I'm going to put that little nut on there and try to get it on there. This is difficult for students. I don't find it to be quite so difficult, at least normally I don't. Maybe right now while I'm trying to demonstrate it, it will be. But I just put the nut on top. I hold it down with my thumb. Where is it now? Hold it down with my thumb, and then I just spin the bottom, and I can continue to hold it and spin the bottom until it's kind of snug. While I'm holding that down, I'm going to snug down the nut on the back side. So just hold that one up on the front with the needle nose pliers, and then there we go. Okay. So there it is. That is the voltage regulator that's intended to be bolted down to the heat sink. There's an extra heat sink in there. Now we can flip it over and solder in. So that's what I'm going to do now. Solder that heat sink in. I'm going to find it for you so you can see it. So over here somewhere, there it is right there. Those are the 3 pins. I'm going to solder those in now. There's 1. There's 2. There's 3. Okay. Now we have the voltage regulator in. What are we going to put in next? In my opinion, the next thing we ought to put in are the SPDT switches. They can be kind of annoying if you're not careful. There's a lot of problems that can happen with these switches, but we're going to put them in. I'm going to pull one out and show you what it looks like. And I need you to compare it against these holes. These holes on the bottom, they have 3 holes. I don't know if you can see it. Let me put it on the board. Maybe you can see it that way. That single pole double throw switch has 5 pins. 2 of them on the outside. They're meant to mount to the board. Well, we don't have mounting holes on this board. So what we do is we snip them off, and I'm trying to show you the mistake that is very easy to make. If I'm not careful, I'll end up snipping 2 of them instead of 1 of them. And students do this all the time. So I show them on the document camera. Make sure you only snip the outermost ones. And of course, those are projectiles. I just heard this one bounce off the ceiling and back down. But you got to do this to all 4 of them. Snip off that. Make sure you have your safety glasses on. Snip off those extra ones. Let me see if I can find the other ones. Here's another one. And here's another one. And here's another one. So we need to trim all of those down. And just do that really quickly. But be careful that you don't clip off one of the... Now this is SPDT, single pole. That's the data pin in the middle. And double throw. Well, the throws, that means the switch has 2 directions, and it connects that middle pole with the 2, either of the outside. Students sometimes ask, why can't we just have a push button switch or an on-off switch? And the reason for that is that we pressurize the middle pin with the power, but if we don't depressurize that middle pin with the ground, it could give us a false reading. So that's what we do. Now, being as obsessive compulsive as I am, I like to line them up so that the little numbers are facing the outside of the board. You don't have to. It's not important. They'll work either direction. Looking for the little numbers, putting them on the outs, making them face the outside of the board. I'm going to set it down. They didn't fall out. What I usually do to hold them all in place is take about 3 inches of tape, and I just pulled it off of my tape dispenser, and I fold one end over because sometimes it gets stuck on the table and I spend 5 minutes getting it off. And I'm just going to tape these down to the board, just like this. It doesn't matter if they're leaning, just tape them down. And you just don't want them to fall out. Then I'm turning the board over, pressing that down a little bit, and now I can solder all of those. Now, as I solder, I'm going to try to make what is known as a solder bridge because, well, they make it so it doesn't work, and also they're fun to get rid of. So here we go. can just get one solder bridge. Oh, is that one? Oh, no, it wasn't. Oops, I made a solder bridge. Okay, now I'm going to try to go with the rest of them. Not make a solder bridge anymore. But if I do, more fun. Now the board's wobbling a little bit. I probably could stabilize the board by putting something underneath the board. So, but I should be able to splice this together pretty well. And notice I'm not too worried about solder bridges. Now, a problem that happens with these switches is when students jam so much solder in there, the solder melts to the other side of the board and messes with the function of the switches. It'll either put a solder bridge on the other side of the board, which is often a reason for the first indication that this thing is working is the green light flashes. But if the switches are messed up, quite often that messes up the flashing of the green light. So students should not be trying to jam a whole bunch of solder in here, just enough to get this thing hooked together. Now, solder bridges like this, I just melt them and tap, and they're gone. So, also there's solder blobs on the top that becomes a solder bridge, and you can heat those up and tap as well. I'm just going through and double checking each of these. There's another solder bridge there. And maybe one there. It's gone. Maybe one here. That looks like that's gone. So now they're all good. And I can go over to the other side and I can take the tape off. And those are in. But students are always asking me, they sure look skiwampus. What can we do now? Well, you just bend them straight. If you don't have too much solder in there, you should be able to bend them straight and they'll work just fine. Make sure they all flip in both directions, and mine do. So it looks like I've got them all in. They're all good. And now we've got those switches in. That was pretty fast. By the way, I'm going fast. I've done lots and lots of these. You don't have to go fast. Take your time. We're going to install something called a potentiometer here, which is a variable resistor, and it has a maximum of 10,000 ohms of resistance, and that variable resistor looks like this. There it is right there. And it fits in the board right here, and I'm just going to put it on the board through the holes that it goes in. We can put them through the holes, and then maybe use the little screwdriver and bend them over again, one way or another. And if you can do that, it might just hold itself in long enough to solder. Even so, if you place it down, it sits kind of flush right now. And now I can solder that potentiometer in place, the variable resistor. Okay. These small holes are going to be the easy ones for students to start with. And then they look at those big gaping holes on the other end and they say, how in the world do you solder those? Well, I start by soldering put the soldering pencil between the two pieces of metal and jam solder underneath it. But the trick to filling that hole with solder, which is what the instructions say to do, is jam a whole bunch of solder in there really fast, and it seems to just fill the hole right up like that. That's the trick to it. Okay, turn it over. We got a potentiometer on there. Seems to be all hooked up, working well, and ready to go. What's next? Let's do the DC jack. The DC jack is this little gadget right here. And it's obvious there's only one direction to put it in, and it is not that direction. It is not, that direction. There's only one other direction it can go, and I think the reason that it goes this direction is because you don't want to plug in the transformer this way and also a battery in this way, and so they sort of get in the way of each other depending on which one you've used. Okay, going to turn it over, rest it on the board, hopefully it'll stay. Looks like it's staying. I'm going to solder that in. Remember, the trick to soldering: filling a hole, jam a whole bunch in real fast. Heat it up, solder, jam a whole bunch of solder in there really fast. Not a single one of these connections have I spent more than 15 seconds on, and I'm running out of solder here. So I'm going to take down to my last little length of solder and jam it in there. And now I've got about an inch of solder left there. So I'll get myself a new piece. And it looks like the jack, the DC jack is in. Okay. Now the next thing we're going to do is put those 9-volt battery connector clips in. And this is a place where a lot of students mess up. Let's talk about that. There's a battery right here. And the battery clips. Push this over, show you the battery. And here's the battery. Here's one of the battery clips. And here's another one of the battery clips. And I want to point a few things out before we move on. Notice on my battery, and all batteries are not like this, but this battery has a plus here. And if I hook this battery up like this, it would be hooking the plus side to the minus side. So we don't want to do that. We want this minus side to be over on this side. Also, when we can't just put these two soldering clips in, these connector clips, we can't just solder them in without the battery, because there is a specific gap between them that if that gap is not there, then the battery won't connect. So we put these clips on the battery, which I'm going to do off camera really quickly. And there they are. And I'm just putting it on, which is what the students do. There it is. Looks like it's all ready to solder, except that it's still plus over negative. And that's wrong. So I got to rotate those clips around to the other side, flip the battery over and plug it in that way. And that's what I'm going to do here. That way I can hold the battery in. It can sit where it's supposed to. The minus is on the minus side. The plus is on the plus side. And the gap between the two battery posts is exactly the right distance. But that's going to fall out. How do I keep it from falling out? Another piece of tape. I grab a piece of tape off of my tape roll and just tape it like that. That holds everything in place so you can solder it. Just tape onto the board, onto the battery. You might want to put something underneath the breadboard to stabilize it while you're soldering. And there it is. You didn't get to see much of that, did you? I soldered all of those in. So the battery's on. I can remove the tape, flip it over, and now those battery posts are in. Okay, so I'm going to remove the battery. Don't need that until later. And what else? Next thing we're going to do is we're going to solder in what we're calling the polarized components. The polarized components, basically that means if you put them in backwards, they're not going to work. Polarized components are some of the capacitors and the LEDs, all polarized. Let's find the capacitors and look at those. Okay, here's a couple of polarized capacitors. We've got another capacitor that's not polarized, doesn't matter which direction you go in. What you notice about those capacitors is that one leg, one of the leads, is longer than the other. That is the positive side, but that's really hard to tell if you cut those leads off, which some people do. But there's also a stripe that you can just barely see here. It's just shrink wrap that they're putting on the outside to hold down the label and stuff. And that shrink wrap has a minus sign on this strip. It's on both of them, and that tells us which side is negative. Okay, so it looks like it's the negative side is the short, and that's pretty standard for components. The negative side is the short side. Where does it go? Well, it's going to go in here because these are, if we read them correctly, let's read them correctly, they are not going to show us. Hold it this way and this way. Is that going to show us? You can kind of see it. It's 100 microfarads. That's what we want. Long side's the positive, short side's the negative, and there's two little round holes, and there's a plus, so the long wire goes into the plus on both of those. Okay, so let's put those in. I'm going to put the long wire into the plus side, short wire into the minus side. Take them, push them right down to the board, hold it in with your finger, turn it over, and just bend those leads to the side, and that keeps it from falling out. Hopefully you can see that okay. Going to do the second one now. Going to put the long lead into the plus hole, the short lead into the minus hole, press it down. It's jumping around. Press it down with my finger, turn it over, and then bend those two leads back. There goes one, there goes the other, and that keeps it from falling out. Other polarized components are going to be the LEDs. The LEDs are going to go into those 4 holes there. Kind of hard to see them. Maybe you can get the glare off of them by tilting it a little bit. There it is. So we got these 4 holes. They have little pluses and little minuses on them as well. And so we're going to find the LEDs. Now you've got 4 red LEDs and you have got 1 green LED. We're going to do the 4 red LEDs first, just showing you those LEDs. Notice that they have longer legs on one side. That's going to be the positive side, but also there's another indication, which I hope, I'm going to zoom in, I'm hoping we'll be able to see if I zoom in really far and show you. Notice, well, let's go from this direction. That's pretty good. Hopefully you can see right here that that is, we call it the rim, and on the rim there's a flat side. It's kind of hard to see. Well, you can see it pretty good there. There's a flat side on that rim. That's always the negative side. That's going to be the short wire. There's the short wire on the rim. So now I know the long wire goes in the plus side and the short wire goes in the negative side. And if I do that on every one of these, then I'll be getting those in the right direction, the correct direction. The long, I don't know if you can see this. Let me move it so you can. The long wire goes in on the plus side, short wire on the negative side. Doing that again, putting the third one in. Long, short, and one more. Hard to see because I zoomed in so far. Maybe you can see these okay. I got all 4 of these in now. I'm going to zoom out a little bit and maybe focus a little bit. Okay, now I'm going to hold all those in and bend those leads to the side on both sides. I got these backwards from each other. Just bending these leads over so that they don't fall out. And then I will solder those in and clip them, but I've still got the green one to do. Here's the green one. It's got a long side and a short side. The long side is the power, and the short side, or the positive, and the short side is the ground. And those leads are almost the same length, but no, one is definitely longer. Putting the green one in. Hopefully you can see that okay. And we got the green one in. Okay. And I'm just going to the back and leaning those over. And now, these are all of the polarized components. So now I'm just going to solder all of those polarized components in. Here we go. Getting my solder, giving myself a unwrapping a little bit of it. Solder pencil. And just starting in on them. That last one had a little solder on the edge, on the tip of the solder pencil, and just dripped down into the hole. I didn't even need to put any solder on the lead. But I did get a blob, and that blob I can just reheat it up here. Reheat this one, and then re-solidify. It looks good after that. I got those. So got all the LEDs in. Here are the 2 capacitors. There goes one. There's another one. Third one. Fourth one. Finally, the LED, the green LED is over here. Jam some solder in on that one. jam some solder in on that one, and I got it. So now I'm going to trim using my diagonal pliers. I tell students maybe put a finger over the top of these so they don't go off and try to land in somebody's eyes, but there's one, another one, another one, another one. Very conveniently are heading toward my hand. There's a little solder bridge there. We'll get rid of that in a minute. Let me get this one. Turn around. Okay. Looks like I got one more there hanging around. Oh, he's just loose. Solder bridge. A little too much blob solder over here. Just heat it up, tap it, and dribbled all the way down, but that's okay. We got it. It's good. Okay. So you can see everything, all of the polarized components are soldered, and hopefully I didn't go too fast for myself on there. If I wanted to, I could have gone back and trimmed down these 3 posts. These are the voltage regulator. There's a couple 3 posts here on the DC jack. Some posts that are sticking out. You can trim all those. That's not a big deal. Once they're soldered in, you can trim them down. All right, so now the board's looking like this. What's the next thing we want to put on this thing? Well, we got all the polarized components. So the next thing we're going to put in are the non-polarized components. For example, I tell students this is not an ibuprofen. Don't eat it, but that is a capacitor. And hopefully we'll be able to zoom in and read that capacitor. Going to zoom in really, really close to it and zoom. And hopefully you can see that says 103Z. Okay. Now I want to talk about that for a minute. And so I'm hoping I have a pencil here that's sharp enough. Okay, that says 103Z. That's not very dark, but maybe you can see it. Now, we read this like color bands on a resistor, so we keep the 1, we keep the 0, and then the 3 is the multiplier band. That means we got 3 more zeros, and that is the value of this thing. And notice on the capacitor, it didn't say any prefix, no milli, micro, nano, pico, femto, anything like that. On capacitors, it's always pico if nothing is listed. Also, the units of capacitors are farads. So we need a 10,000 picofarad capacitor. The problem is there is no place listed on this board for a capacitor that's a 10,000 picofarad. We have to move the decimal over, and now we've got 10. Can we still see this? And if we move over 1, we're in the nano range. So if we move the decimal over, now we got 10 nanofarads. There's nothing like that on the board either. So we're going to move the decimal over one more time, give myself a little space, get that, past that blob. So I'm going to move the decimal over 3 more places. That'll give us 0.01. I could put the 0, and then it would be microfarads. And if you look on the board, let's pull it over here, there is a place for that size of capacitor. And it, again, it's non-polarized, so that's where that one goes. That is the 0.01 microfarad capacitor. Remember, it's not polarized, so I can stick it in either direction. Don't care which direction it goes. And just pressing it down and trying to get it on the screen so you can see it. Pressing it down, I'll just pull it from underneath as well. Get it as far down as I can. It doesn't have to be against the board. When I'm satisfied that it's down far enough, I'm going to the back side and bending those wires back to kind of just hold it in place. Right there. Okay. So that's one of the non-polarized components. The rest of the non-polarized components happen to be resistors. I'll zoom out a little bit to look at the resistors. Here they are. Let me get rid of this confusing thing on the board. There are the resistors. There they are. I think it was out of ease, out of efficiency, that they chose to make all of these resistors the same. These are backwards for reading, first of all. If you can see that, that's brown, which is a 1. Black, which is a 0, so that's a 1, 0. Red, which is a 2, that means the multiplier band. That means these are 1, 0, 0, 0 ohm resistors. These are 1,000 ohm resistors, also known as 1K ohm resistors. We're going to use all but one of them. So I'm just taking the tape off one side, just pulling the tape off the other side, and now I've got them all like that. What I'm going to do, doesn't matter which side you do, but because I'm obsessive compulsive, I'm going to find that brown side. And I'm going to take that brown side like this, that is the brown band, and I'm going to bend that over so it is now parallel with the other pin. And I need a total of 5 of those. Okay, now I've got 2 resistors left. 5 of them are bent, like I just said. I'm going to bend these off the view of the camera, but I'll put it back on so you can see what this next one is bent like. It looks like this. There's one more resistor there that's just a spare in case we mess things up. Just going to plop that in the box. So I like these resistors. They're going to be what we kind of refer to as stand-up resistors. And I always have had students put those resistors so that the wire faces towards the bare wire faces towards the switches. And I got thinking about that, and I thought, you know what? For grounding purposes, maybe that's a little too exposed. I'm just holding it down and bending the pins on the back side, putting the next one in. Next one. Sliding it in there. And bending the wires underneath. One more. Goes right there. And bending the wires underneath. We got one more. That goes on the green resistor. I think I will make that wire face inward. And so there it is. I'm going to hold it down as I turn it over and spread the leads on that one. We got one more. This one goes in the hole marked R6, resistor 6. This resistor is used by the 555 timer to give us the square wave pulse. Pressing that down to the board on the back side, bending those pins over, and now we've got that one in. Okay, so turn it over and soldering and clipping all of those on the back side. I'll reset it so you can see a little better what I'm doing. But there it is. And I'm going to start soldering each of these. Soldering everything in. Hope you can, yeah, I guess you can see that okay still. There's this one. And that one. And looks like I've got these last 4 to put in here. Two more to go. Students sometimes say, how come my solder gets stuck? And what do I do? To get solder unstuck, you melt it. Okay, I got all of those. And I think I can remelt those after I clip them. So now I'm going to go and clip everything off the back side of the board. make everything short. Maybe I'll go over to the voltage regulator, trim that down. Maybe the power jack, trim that down. Hope you can hear me and drifted a little bit far from the mic. But if nothing else, you can see what I'm doing. Looks like I got another email. That was loud. Okay, got everything trimmed down pretty well. This one is still a little long. And what the heck, I'll go over here and I will trim the voltage regulator pins as well. And, I don't know, these power jack pins, maybe. And variable resistor pins. I think I've pretty much got everything trimmed off of that bottom of the board there. Okay, so now we've got all of the non-polarized components in. Those are all of the resistors, the 0.01 microfarad capacitor. Doesn't matter which way they go, but I like them to go a certain way so it looks nice on the board. Because, you know, I'm building a little space station here. So anyway, let's see. I think I have explained all of that. Okay, the next part is called header pins. But before I do that, I want to point out that some of these components are a little skiwampus. You can bend them in one direction and make them stand up a little bit better. You can remelt if you want them to go the other direction. I was going kind of fast, but I think I will try to remelt this one and bend it if I can. Yeah. So I've remelted that and I bent it up straight a little bit. And, you know, they're pretty well standing up. Maybe the switches, maybe I'll bend those out just a little bit so they stand up straight. And we're moving right along here. Okay, so the next component are called headboard or, header or breadboard connector pins. And this is what we've been given. And this is quite often a problem for students because I'll tell you what I'm about to tell you, and then for some reason, even after I tell them, they forget how to count. What I want is a total of 3 groups of 4. So I'm taking the needle nose pliers. There's a little channel right down in there that makes this weaker. And so if I grip it right here and then bend, I've got a group of 4. Now I also need another group of 4, but there are 6 here. I also need a group of 2. So I'm just going on the group of 2, and there's my group of 2. Over here, I got a group of 5. I need to take one of those off. So, hold the 1. Okay. We're going to use these 3 groups of 4, this group of 2, this group of 1. Just throw it in your box. Won't be using it. Okay. Now, I do something that I think really helps my students that I haven't seen a lot of other people do. And that is I'll take a breadboard, a short bread. Is this a short one? Yeah, I think this is a short one. One of the short ones you can buy. And then I'll slice it in half and take the side rails off of it. When I do that, I'm going to take these long pins and I'm going to press them right there. Short ends of the pins are sticking up. The long ends of the pins are going down into that piece of breadboard. Leave one hole between these two and put the second group in there. Leave 5 holes between this group. Press the next group in like that. So we got 4, 1 hole, 4, 5 holes, and the last group of 4. That breadboard holds them in place, so now I can simply put the board on those pins, the breadboard companion on those pins. I don't know if you'll be able to see me put this like this, but it just fits right in there like that. maybe on the other side I'll prop it up with a battery or something. Looks like. There we go. So now the short pins are going up through the bottom, through the board. The little plastic retainer, like is on this group of 2, is underneath the board, and those pins are going to be pointing down. And I need to solder all 3 fourths is 12, all 12 of those in place. What I'm soldering here is going to be my access to 5 volts. This next one says V in, voltage in. That's going to be 9 volts. This says clock, and this one says 0 volts. So when I need 0 volts, I will attach to that. Oh, look. Solder bridge. And I just wiped it out of there. Okay, so now this, if I want to hook up to light 4, I will connect there. Light 3, I'll connect there. Light 2, connect there. Light 1, I'll connect there. And those are just they've turned out to be bulbs on the top. So I'm just heating them back up and making a solder bridge, and those are connected. Going to do the last 4. These are connections to the 4 switches. So switch 4 there. Switch 4. Switch 3 with a big blob. Switch 2, another big blob. Switch 1, a big blob. And the blob has just followed me all the way down. And I just pop it off of there. And soldering pencil might be a little hot. But those are all now in, and I can just pull them out of the breadboard, and they are hooked into the breadboard companion. Now, students will all keep this breadboard because they can now put that breadboard companion on there, and they have 2 connections to each light, 2 connections to each switch, and 2 sources of power, ground, clock. This VIN, this voltage in, I almost hesitate to even put that on there because voltage in is 9 volts, and that will burn up anything that we use, any chips, any LEDs, any components that we use. 9 volts is generally too much for that. But so far we've been okay, and I've just told students, never use that one. 9 volts, okay? So VIN is the original voltage that you put in. It might be regulated down to 9 volts, but I don't think so. If you have a transformer that you plug in here that's more, that will be the voltage in, and I think it'll be even higher. These holes over here, there is a little add-on that you can put on here that I've never used. It's for a programmable chip. Not much information is given about it. In fact, I wonder if I still have that up. I can actually show you what I'm looking at. Here's the breadboard companion. I was going to show you this earlier. This is the breadboard companion pricing structure for this year. So there is a PLD companion, programmable logic device, that snaps on, and but I usually buy the breadboard companions. This year I bought, I don't know, about 60 of them. So my price was $21.50 each, and my school generously buys those for the students each year. It's been very nice. But the fewer you buy, the more you pay. And then you come down here, and this is how many kits you bought, and the flat rate cost of shipping for each one of those. You can also buy other things from this company, and I've used them for years. They're really a great company. And so I wonder, here is their website here, and it's just Breadboard Companion. And so if you're interested in what they have or want to contact them or find theirs, just look up Breadboard Companion. Okay, so don't need that anymore. Here's our breadboard companion. Is it completed yet? No, not quite. We just put on the header pins. We've got a couple more pins. Remember that group of 2? TP1 and TP2 here. You can see them right here. They'll stand for test pin 1 and that's test pin 2. And the purpose of those pins is to be able to send a signal out to an oscilloscope. so you can see the sine waves that this thing generates. Now, it generates some pretty dirty sine waves, and that's what that other chip does. I'll talk about that in a minute, and I'll show you what those sine waves look like as well in just a minute. But what I'm going to do now, I'm going to put this group of 2 in here like this. That is how it goes, and we're going to solder the bottom. But how are we going to keep that from falling out? Well, it's pretty easy. I just put a piece of tape on there like that, and that just press it down, holds it in until I can get it soldered in. So now I'm going to solder that one in, and notice that its plastic is on the top of the board, whereas these other pins, their retainer plastic is on the bottom side of the board, and the short pins always go through the board. And another solder bridge there. There it goes. So now these pins, these test point pins, they're on the top of the board now. Next and last things we install are going to be these chips. Now, this small chip here, this small integrated circuit, is a 555 timer. For it to work, it needs some capacitors. The output will be indicated on that green light. There it is. And so it's going to need the 3 capacitors, this resistor. They all go with, the resistor here goes with this light because the LEDs only use about 2.5 volts. And so the resistors reduce the voltage from 5 volts down to 2.5 volts. So we have this little 555 timer chip, and it has to go in the right direction. And you can almost see that little notch in there. That's the notch. And that has to go the same way as the notch on the breadboard companion socket, which is that little notch right there. You point to that one. Because if you put this in backwards, it's not going to work. There's the little notch there, just below the first 2 5s there. Now I'm going to have to do the same thing with this larger socket. So I'm going to take that chip. Where'd it go? There it is. I'm going to pull that chip out of the sponge. There it is. This is a MC, that means it's Motorola. 74, that's for industry as opposed to military. F14, it's the 14 that matters. This happens to be a group of 6 inverters. And actually, we're only using 2 of them. But these inverters also have something called a Schmitt trigger. But this is the Schmitt trigger. Now, what happens with that 555 timer is that raggedy-looking signal that's coming out. And what it's doing is simulating a very rough sine wave, which this chip is going to smooth out into a very solid square wave. So it's actually taking this and it's rising up and it's turning it into a very square wave. Unfortunately, it's inverted, which is basically what this chip does. It's using inverters and it's using the Schmitt trigger to smooth out this wave. We're going to run it through 2. That cleans the wave up twice and also flips it over again so that the square wave is going the correct direction. And what I need to do is, because these are not 90-degree angles on these pins, so I'm just going to squeeze them all just gently so that they're roughly 90 degrees. I could use my needle nose pliers as well, but that might be close enough. Looking for the notch, because I got to make sure that that notch goes the correct direction. It's not a very good notch, but that dimple in there, that is also on the correct side. In fact, that dimple is generally above the pin number 1. See that dimple there? That means this is pin 1, 2, 3, 4, 5, 6, 7. 7 on these 14-pin chips is almost always the ground. 8, and then going up the other side, 9, 10, 11, 12, 13, 14. 14 is almost always the power. I have never seen one that's not, but I'm not going to say they all are. And then you can see the little dip there, little notch there. So now I'm going to set this gently on top of the circuit slot. And before I press it in, I'm just going to take a quick look to see if it looks like all of those pins are going in their particular slot. Then I'm going to press it down in. And sometimes, if this thing doesn't work, it's because these chips aren't pressed down in far enough. Moment of truth. Moment of truth. Going to zoom out. This thing is done. Just need to connect the battery. And my first sign of success will be the flashy green if my battery's charged. And I got no flashy green. So, something's wrong, but I'm going to try a different battery. I'm going to plug that in, and I'm still getting nothing. Now, I know the battery's good. Green light should be flashing. I've turned the potentiometer knob up and down. And so the first thing I'm going to check is, of course, is the battery dead? The second thing I'm going to check is, have these battery posts been installed backwards? So I'm going to flip it back over, and I'm going to look. Oh, well, let's see. Nope, they're the right direction. I know it's the right direction because I got negative on here, and I got negative there. And so I can plug that in. It's the right direction, but it's heating up, which means there's a connection between power and ground somewhere, and it's heating it up. So I'm going to disconnect the battery because it's getting kind of toasty. Now, what could it be? What else should I check? Okay. Are these integrated circuit chips seated correctly? Now, they're not. I see a problem right there. This chip has been inserted backwards. I wasn't paying very good attention. I'll bet that's my main problem. Now, you've got to be careful when you pull these things out. Where's my screwdriver? Because you pull them out wrong. If they really resist strongly, you could end up with 14 little pinholes in your finger. So if I can just get that screwdriver under there and wobble it back and forth, I can get this out of there without too much problem. Now, I'm going to check it. I'm going to turn it upside down. Make sure none of the pins are folded over. They don't seem to be. But I'm going to reinsert this the correct direction. By the way, I will fess up, I really did make this mistake I didn't make it on purpose. This was a mistake. But it was a fortunate mistake because it allows me to troubleshoot. Once I've turned that chip around, I'm going to plug the battery back in, and I still got no flashy. Turning my dial up and down. Nothing. Testing the heat. No, I'm still getting heat in the variable resistor. So just going to press those in. There's something in there that's connecting the power to the ground. And I'm going to check those switches again because they could still be a problem. I'm going to flip them all up. There it is. And all down. What happened? The light started flashing when one of those switches was flipped. Was it that one? No. Was it that one? No. That one? No. That one? No. Might be too hot. Turn them all on. Let it cool for just a second. And it's flashing again. Still flashing with one off. Still flashing with two off. Still flashing with three off. And not flashing. So it's that last switch there. The others. And I know my voltage regulator is getting hot. There's a problem with this last switch down here, because when I flipped that switch on, the light went flashy. There's a problem. Okay, so what do I do about that switch? Well, I flipped it over, I'm looking at it, and it looks, I don't see anything terribly wrong with it, but I just bet that particular switch, which one was it? It was this one, S4. I'll bet that switch is grounded underneath, got maybe a little bit too much solder on it. Common problem. I'm actually going to hold the switch, the offending switch, with my needle nose pliers, and then I'm going to press against the board with my finger. I'm just going to melt the solder as I push against it, and sometimes it destroys the switch, which is fine. So at this point, my cable came out of my microphone, and so it went, quiet. But it's fine because I have more switches. I can easily put another switch in there if I need to. Hopefully this is loud enough. I don't know if it is or not. In any case, you also maybe have noticed that blob in there. That blob was the cause of the whole problem. Okay, next what I'm going to do is focus on the actual place where the switch came out. It's hard enough to get a component out, especially the more pins it has, the harder it is to get out. But what's also just as hard is if the holes that the pins came out of have solder in them, then you can't get the component back in. So over the years, as I've done this, I have devised a way that works for me to get those holes cleared out, and I'll be showing that in just a second somewhere along this video. But what I do is I take a tube from a ballpoint pen, and then I heat up underneath the holes, and I have the tube in my mouth, and I focus the end of the tube, or put the end of the tube over the holes, and then I blow out the hot solder from the holes. So it's heated from underneath, and then I blow out the hot solder from above. That's what I'm doing here, and hopefully it'll work. Eventually it does, and I think I clipped all that out, but you will see in just a moment that all of those holes have been cleared out. All right, with all of that dexterous motion, I accidentally unplugged my mic. I hope that wasn't a problem for a long time. I have to re-record all this. Going for the third one. Where is it? Here it is. Okay. That's all it took. And you can see those holes are all cleared out now. And taking the blobby out of there. And giving it a good stare through my glasses. That looks good. I'm going to put that back in. So that's the offending switch. And I'm going to grab some tape and just kind of tape it in place. Just needs to hold there long enough for me to solder it back in. Looks like the pins are poking up through. There's one. There's two. There's three. All soldered in. Good to go. There it is. Turning it on and off. And how did I know it was going to be a switch? Experience. So now I plug it in and zoom back, and the light is flashing, and hopefully this chip is not heating up, and the switch itself has no effect on the light. Okay, so got it working. But there are a couple of the other tests that we should do really quickly before we call this completely done. And that is, I'm going to press it back into this block and do a quick switch and LED test. To do that, I'm going to need a length of wire, just some random length of wire. What I'm going to do is turn all these switches on. And I'm going to plug this wire into switch 1 on this board, and then I'm just going to strum down on these posts here, and the lights should turn on. And so you can see that they all turned on, so I know my lights are working. Quick test, just keep testing this voltage regulator to see if it's getting warm, and it's not. So that switch that we cleaned off and reinserted is working. Now I've got the lights I know working. Now I'm going to test all of the switches. They're all on. So that one, and that one, they're all turning on the same light, but they're all on. If I wanted to do another test, I could plug into the switch and the light. Okay, so I'm actually on switch 2, and that's what's connecting to light 1. Let's do each one again. Here's 1. It works. 2. It works. 3. It works. 4. It works. I declare this thing working. One more test we might do, but it isn't necessary, I don't think. I think we'll be fine. We got the 5 volts. Well, there is a test we can do. It's similar. It's suggested we use a multimeter to do this, but you see that clock? I'm going to connect to the clock there, and then I'm going to connect to the lights, see if I'm getting the clock. So now they're both flashing to the clock. I'm accidentally touching the other one as well. But notice they're flashing. One's inverted from the other. And so this clock is an inverted output as well. Okay, so we know that's working. I could plug it into the 5 volts. Do not plug it into the VIN. Plug it into the 5 volts, and I could do any of these lights, and we know that that 5 volt connection works as well. So there it is. We built it. It works. We troubleshot it. It works. What else could we have done to troubleshoot it? After the switch, well, let's go through. We checked to see if the battery was dead. We made sure the battery posts weren't backwards. We checked the switches to see if they were affecting the flashing, and certainly they were. Sure enough, that was the problem. We figured out which switch it was by isolating the switch, pulled that switch out, saw the blob on the bottom, removed the blob, cleaned out the holes, put the switch back in. The darn thing worked. Are the ICs properly seated? That is, these 2 chips. We would just make sure they're pressed down. We might pull them out, make sure they're the right direction, make sure there's not a pin folded up underneath them, and or a pin that's outside. We would do polarity check again on all capacitors and LEDs to see if they're all the correct polarity. If anything's in backwards, they weren't. We would do a quick resistor check. We'd unplug the battery and then just do a quick resistor check with a multimeter to see if if there's resistance on each of those resistors. After that, we might swap out the board. We might try a different board. Now, I've seen that before. I've actually had a defective board where I put a bridge wire across from either the power, this is the power here, to this pin, which is the power. So from this power to this power, I did a bridge before, and then from ground, and the middle one is ground, and that bridge, that wire bridge that I put there, worked. What else? I would check all the soldering connections on the bottom of the board and make sure that everything on the bottom of the board is working. I'd probably do that before concluding that it's a defective board. Defective board would be my last possibility. We just did a voltage check. We didn't use a multimeter for the 5 volts and the 0 volts. We would use a voltmeter for the VIN. Since I never use it and since the other ones worked fine, I'm not even going to worry about that. Then we checked the switches in the other LEDs. That's what we did, checking the switches in the LEDs here. And we tried the clock with a flashing LED. We've done every kind of troubleshooting we can think of on this thing, and it works. And that's pretty much troubleshooting on those things, and that is all there is to getting this thing going. Okay, now I got it working, but I realized there is one thing I haven't soldered in here, and I'm going to show you that now. What I need to do is find one of those wires that I clipped off. We clipped off tons of them, so there should be several. There's a wire right there. Show you on the screen here. There it is. I need to bend that into a U shape, so I'm just bending it like this. And I'm going to put it in this connection, or this location that is labeled GND. And you can see it's gone in like that. Okay. So I'm going to bend the underneath back sideways, just so it stays long enough for me to turn it over and solder it in place. Take that breadboard off, zoom in, and there we go. I had to turn my soldering pencil back on. So there it is right there. Solder that and that. There it goes. Okay, diagonal pliers. I'm going to trim that. Looking at it from the end now, it's got a little loop. Easy loop to forget about. And let's talk about that loop for just a second. That loop is going to be convenient ground for my testing probe. When you hook this probe up, you hook one red to the positive side, black to the ground, and then this probe, once you've done that and set it correctly, set it to TTL, I think I've got TTLs, but what happens is it will give a low-pitched sound if it's ground that it touches at the end of the probe, or a high-pitched sound and red as if it's a powered connection. So this little ground loop is meant specifically for this probe. Now I generally will put this probe on the breadboard itself. I'm going to give it, I don't know, 5 volts. See if I can get hold of 5 volts here somewhere. Okay. Now, what it's supposed to do is give me a, let's see if I can get that all on camera. I'm touching ground. And it's telling me I have an active ground. I can touch power. And because that's the same power that I'm hooked up to down below, well, there it goes. So that's power. Now that's useful when I'm following the wires of a circuit back and trying to see if they're connected to ground or power connected correctly. Do they have power going through them? So that's what that ground is for. It's just an easy, convenient place to ground this thing. Breadboard companion. Students love them. They like owning them. They like making them work. They like learning to solder. They like learning what all those components are as they put them in. They enjoy this. And they love keeping them and taking them home at the end of the year and using them on their own projects. Okay, this is Aaron Jerome. Thank you for watching. Jerome Electronics with an X on the end. Please give me some feedback if there are ways that I can improve this video. Thank you. Bye-bye.